Welcome to the deep dive. We are plunging headfirst into the technology, powering some of the most talked about AI today. Large language models.
Yeah, LLMs.
And specifically, we're unpacking the core architecture that makes them tick the transformer.
That's right. Our mission in this deep dive, guided by the insightful sources you shared, is really to pull back the curtain.
Yeah.
We want to understand what's truly happening inside these models, focusing on the fundamental components and the process by which they actually learn.
And you've given us some fantastic material, drawing heavily from the 3 Blue 1 Brown YouTube channel.
Yeah.
Those videos have this incredible gift for taking intensely complex ideas
You really do.
and making them visual intuitive, breaking them down step by step.
It's easy to feel a bit overwhelmed by terms like embeddings or backpropagation at first glance, but the way these sources approach it is just so clear.
Right.
We're aiming to carry that same spirit into our conversation today.
Exactly. And the whole modern wave really traces back to one seminal paper from 2017, Attention is All You Need, which first laid out this transformer architecture.
Yep, that's the one. So to understand the transformer, we really need to start with the bedrock it's built upon, the foundational ideas of neural networks.
Okay, let's do a quick recap of those basics then, drawing on the intuition from your sources. At its heart, a neural network is, well, it's a series of layers.
Right, layers.
Each layer is made up of simple units, often called neurons, and each neuron just holds a number, typically between 0 and 1, right? It's activation.
Think about that classic example the sources walk through recognizing handwritten digits.
Oh yeah, the MIST example.
Exactly. You have an input layer where activations might represent pixel brightness, then hidden layers, and finally an output layer where ideally only the neuron corresponding to the correct digit lights up.
And the connections between these neurons are key. Activations in one layer determine the next layer's activations via these connections. Each connection has 2 adjustable parameters, a weight and a bias.
And the calculation involves taking a weighted sum of the activations from the previous layer, adding a bias, and then applying a simple nonlinear function, something that squishes or clips the result.
Like sigmoid, or more recently, ReLU.
Yeah, newer networks often use the ReLU function, which just sets negative values to 0. Very simple, very effective.
Right, and learning in this context is purely mathematical, isn't it? It means finding the absolute best values for all those weights and biases so the network gets the task right as often as possible.
And even for that relatively simple digit network, the sources point out it has around 13,000 weights and biases to tune, which sounds like a lot.
It does.
Until you think about scaling that up to language models with billions or even trillions of these parameters.
Which naturally brings us to the crucial question. How does the network figure out the right values for all those parameters? How does it learn?
Okay, so this is where the optimization process comes in, primarily through gradient descent and backpropagation.
Right. You need a way to measure how poorly the network is performing first. That's the cost function.
Exactly. It's a single number that tells you how lousy the network's current settings are, based on how far its output is from the correct answer on training data.
Like squaring the difference between what it guessed and the right answer.
Yeah. As your sources show, it's often based on the squared difference between what the network outputs and what you wanted it to output, averaged over many examples.
Okay.
And the goal of learning is simple. Minimize that cost function. Get that error number as low as possible. Gradient descent is the strategy.
I love the visual analogy here, picturing the cost function as this hilly surface in this massive space defined by all the parameters.
High dimensional space.
Gradient descent is like rolling a ball downhill. The gradient is a vector that points in the direction of steepest descent. So you take steps in the opposite direction, the negative gradient.
To find the quickest way down to a minimum. Or at least a minimum.
Right, a local minimum usually.
And the insight from the sources is that the gradient vector doesn't just point downhill. The magnitude for each parameter tells you which specific weight or bias, if you nudge it, would decrease the cost the most.
Ah, the bang for your buck.
Exactly, the bang for your buck when trying to improve performance.
But calculating that gradient efficiently for a network with many, many layers,
Yeah,
that sounds like the hard part.
it is, and that's where backpropagation comes in.
Okay.
Backpropagation is the algorithm that efficiently computes this gradient through the network layers. The intuition given is that for each training example, say a picture of a 7, You can figure out how every single weight and bias should be adjusted, ideally to make the network better at classifying that specific example.
So it's like asking each example, what changes do you want?
Kind of, yeah. And this desired change propagates backwards through the network layers.
And the actual update to the parameters is the average of these desired nudges calculated across many training examples.
Yes, or more practically for large data sets, on a mini batch of examples. This is stochastic gradient descent, or SGD.
Right, SGD, faster, but maybe not as direct.
It's faster computationally,
Yeah.
though the sources humorously compare it to a drunk man stumbling aimlessly down a hill.
Yeah.
It still trends downhill overall, just not in a perfectly straight line.
So at its core, training these networks is fundamentally about using gradient descent and backpropagation to minimize that cost function
Yeah.
using vast amounts of training data. That's how the network settles on its billions of parameters.
Precisely. Okay, so with that foundational understanding of how basic networks learn, let's apply these ideas to the architecture that powers modern LLMs, the transformer.
Right. GPT, for instance, stands for Generative Pre-trained Transformer.
Yep.
The core task we're looking at is taking a sequence of input text and predicting the most likely next token.
And tokens, as the sources explain, aren't just whole words. They can be subword chunks, punctuation, or even represent other modalities like images or sound in more advanced models.
Okay.
The very first step is converting these input tokens into high-dimensional vectors called embeddings.
Numbers again.
Always numbers. This is done using an embedding matrix, often called WE, which is learned during training. It's essentially a giant lookup table where each token gets mapped to a unique starting vector.
Here's where it gets really interesting, though. The sources show beautifully how directions in this high-dimensional embedding space can actually encode semantic meaning.
Yeah, this is fascinating stuff.
They give examples like the vector difference between woman and man capturing the concept of gender, or how Italy minus Germany plus Hitler lands near Mussolini.
It's mind-bending. And dot products between vectors can measure how aligned they are with these meaningful directions.
So these initial embedding vectors, they then flow through repeated layers or blocks within the transformer.
Exactly. The network's goal in these layers is to process these vectors so they soak up context and general knowledge, becoming much richer representations of the input text than just their initial token meaning.
It's important to note there's a practical limit, isn't there? How much input the model can consider at once. Its fixed context size.
That's right. For something like GPT-3, that was 2048 tokens. That defines its working memory for understanding the current situation. Anything before that is, well, forgotten for that prediction.
Gotcha. Okay, so after passing through all the layers, the final vector in the sequence is used to predict the next token. How does that work?
This uses an unembedding matrix, WU. Think of this as doing the opposite of the embedding matrix. It takes that final context-rich vector and translates it back into a list of raw scores.
Logits.
It's called logits, yeah. One score for every single token in the model's entire vocabulary. Could be tens of thousands of scores.
And those raw scores aren't probabilities yet. To turn them into something we can sample from, you apply the softmax function.
Correct. This takes the logits and turns them into a probability distribution over the vocabulary numbers between 0 and 1 that sum up to 1. The token with the highest probability is the model's most confident guess.
The sources also mention a temperature parameter you can apply here. What's that about?
Ah, yes. The temperature is a clever trick during generation. A lower temperature makes the highest probability tokens even more likely, leading to very focused, predictable output.
More deterministic.
Pretty much. A higher temperature flattens the distribution, making less probable tokens more likely to be chosen. This results in more varied, sometimes creative,
Or sometimes nonsensical.
or sometimes nonsensical output. Exactly. It controls the randomness.
And generating longer text is just repeating this process, right? You sample the next token based on that probability distribution, add it to your input sequence, and run the whole thing again to predict the next token after that.
Yep, it's an autoregressive process. Feed the output back in as input.
Okay, so the sequence of embeddings flows through these repeated transformer blocks. What exactly is inside these blocks doing the heavy lifting?
The sources highlight two main types of operations, attention and multi-layer perceptrons, or MLPs.
Let's dive into attention first. It's often called the heart of the transformer.
It really is.
And for good reason, it sounds like. Its purpose is crucial.
Yeah.
It allows every token in the sequence to dynamically interact with every other token,
Even distant ones.
exchanging information and updating its meaning based on the context provided by all those other tokens, no matter how far apart they are.
This capability is vital for resolving ambiguity and understanding relationships. As the sources illustrate, knowing the context differentiates mole the animal from mole the spy,
Right.
or ensures, tower refers to the Eiffel Tower when mentioned in Paris. The word's initial embedding needs to be refined by its surroundings.
Okay, so how does it do that? The mechanism uses three learned matrices, right? W query, W key, and W value.
Correct. Each token's current embedding vector is transformed by these matrices into three distinct vectors: a query vector, a key vector, and a value vector.
And the intuition the sources provide is spot on here, I thought. Think of a token's query vector as asking, what information do I need from other tokens?
And its key vector is like saying, here's the information I have to offer.
And its value vector is the actual chunk of information it might pass along if needed.
Exactly.
So, how do tokens decide which information is relevant? How does the query find the right key?
You compute the dot product between each token's query vector and every other token's key vector. This creates a matrix of scores indicating how relevant each word's information, its key, is for updating every other word, its query.
Like the example of fluffy and blue keys aligning strongly with a creature query.
Precisely. High dot product means high relevance.
These raw relevance scores are then normalized using softmax,
Usually row-wise, yeah.
turning them into weights that sum to one the attention pattern. This pattern shows exactly how much attention each token pays to every other token when updating its own representation.
And during training, there's a critical step called masking.
Ah, right, to stop it cheating.
Exactly. Before the softmax, the scores between a token and any future tokens in the sequence are set to negative infinity. This forces their attention weights to 0, ensuring the model doesn't look ahead when predicting the next token. It has to base its prediction only on the past.
Makes sense. And the final step is how the embeddings are updated.
Right. The change that gets added to a token's original embedding is a weighted sum of all the value vectors in the sequence.
Okay.
And the weights for this sum are precisely the attention pattern calculated for that token's query. So it pulls in information from other tokens based on how relevant they were deemed to be.
And this update is just added to the original vector.
Typically, yes. It's often via a residual connection, adding the change back to the original.
And it gets even more powerful with multi-headed attention, right?
Yeah.
Transformers don't just do this once per layer.
No. They run many attention calculations in parallel, each with its own set of learned Q, K, V matrices. Each head can learn to focus on different kinds of relationships.
Like grammar versus meaning.
Potentially, yeah. Maybe one head looks for grammatical dependencies, another for semantic links, another for tracking entities across long distances. The final contextual update is the sum of contributions from all these different heads.
Wow, okay.
And a major practical advantage of attention, highlighted by the sources, is its parallelizability. Computing all these dot products and weighted sums can happen simultaneously, making it incredibly efficient on modern hardware like GPUs.
Which is absolutely essential for scaling up these models to billions of parameters.
Couldn't do it otherwise, not practically.
Okay, so if attention is about letting tokens talk to each other and gather context, what about the other main component in the transformer block? The multi-layer perceptron, or MLP.
Right, the MLP. Unlike attention, the MLP processes each token's vector entirely independently.
So vectors don't interact with each other within the MLP step itself.
No, it operates on each token's representation in parallel. Think of it as applying the same learned transformation to every token's vector, but separately.
The core computation is structured somewhat like our initial basic neural network layer, but with a specific shape.
Yeah, it's typically a two-layer feed-forward network. A vector comes in, it's multiplied by a large up-projection matrix. Whoop! A bias is added. A non-linear function like ReLU or GELU is applied.
Which squashes or clips things.
Right. Then it's multiplied by a down projection matrix, W down. Another bias is added, and the result is added back to the vector that came into the MLP block, again, usually via a residual connection.
Okay, so what role do these MLPs play? If attention is context, what's the MLP for?
Well, the sources suggest they provide the capacity for storing facts and general knowledge the model learns from its training data, kind of like the model's memory bank.
How? The toy example using Michael Jordan and basketball from the sources helps illustrate how this could work, maybe.
It's a good intuition pump, yeah. The idea is that the rows of the WEP matrix can act like sophisticated feature detectors. Maybe one row learns to strongly activate when the input vector represents Michael Jordan. And the nonlinear function, like ReLU, acts a bit like an AND gate in this analogy. It allows a specific neuron in the higher dimensional intermediate space to activate only if the input vector aligns strongly with the feature the whoop matrix is looking for.
So the Michael Jordan neuron fires up.
Right. Then the columns of the Widgeon matrix represent directions in the embedding space. If that specific Michael Jordan neuron is active, its corresponding column from way down gets added to the output vector.
Ah, potentially adding the basketball direction.
Exactly, thus associating Michael Jordan with basketball through this mechanism. That's the idealized picture.
But here's where the interpretability gets tricky in large, real-world models, as the sources point out.
Very tricky. Individual neurons rarely have such clean, single meanings. It's usually much messier.
Which leads to this fascinating idea of superposition.
Yeah, the hypothesis that multiple independent concepts or features might be encoded in complex, overlapping combinations of neurons, not one neuron, one concept.
And this could be leveraged by the high-dimensional space itself. The sources hint at the Johnson-Linden-Strauss lemma.
Right, which basically says that in very high dimensions, you can have lots and lots of vectors that are all nearly perpendicular to each other.
So there's lots of room to encode many different ideas without them interfering too much, even if they share neurons.
That's the thinking. It might help explain the surprising scaling properties of these models, why adding more parameters and data keeps improving performance. The high dimensions offer a lot of capacity.
But it's worth noting, when we tally up where the parameters live, the MLPs account for the largest chunk.
By far. Roughly 2/3 of the total parameters in a model like GPT-3 are in those MLP layers.
Right. If we quickly tally them up, you've got the initial embedding and final unembedding matrices, each adding maybe hundreds of millions of parameters depending on vocab size and embedding dimension. Then the attention heads across many layers, with their Q, K, V matrices adding billions.
Yep, billions there.
And the MLPs, with their large up and down projection matrices across all layers, contribute the bulk, pushing the total for a model like GPT-3 into the neighborhood of 175 billion parameters.
It's a mind-boggling number of knobs being tuned during training.
It really is. Coming back to the learning process itself, the sources share some fascinating observations from training. Even with the relatively simple digit recognition network,
Yeah.
while it learned to classify perfectly, visualizing the weights didn't reveal the clear edge or pattern detectors researchers might have intuitively expected.
Right, they looked almost random, didn't they?
Yeah. It suggests the model's learned solution isn't necessarily aligned with our human intuition about how the task should be solved. It finds effective patterns, but maybe not the ones we draw.
Which is a common theme in deep learning interpretability. The solutions work, but how they work isn't always obvious or human-like.
And that experiment contrasting training on randomly labeled data versus structured, correctly labeled data is telling too.
Oh, yeah, that was interesting.
The model could memorize the random data, achieving high training accuracy, but training on structured data allowed it to find good performance much, much faster.
Which strongly suggests there's a structure in the optimization landscape, that hilly surface we talked about, that corresponds to the structure in the data itself.
So the model isn't just randomly searching, it's guided by the real patterns in the data towards good solutions.
It seems that way. It exploits this structure. Even if the features it learns aren't neatly interpretable by us, it finds good local minima faster when the data makes sense.
So we've taken quite a journey in this deep dive, starting with the core idea of neurons and how networks find parameters by minimizing a cost function through gradient descent and backpropagation.
Building blocks.
We then dove into the transformer architecture, how tokens become embeddings, how attention allows tokens to gather context from the entire sequence,
The key innovation.
and how MLPs likely provide capacity for storing features and knowledge, potentially through this idea of superposition in high dimensions.
It feels incredibly complex when you look at the scale, the billions of parameters.
Definitely.
But as the sources show so well, the underlying ideas, weighted sums, nonlinearities, optimization, build logically upon each other. It's layers of relatively simple operations.
We've relied heavily on the visual intuition from the source material, and honestly, seeing these concepts animated really is the best way to grasp them.
Oh, absolutely. We highly encourage you to explore those videos further if you haven't already.
Seeing the vectors move, seeing the attention patterns light up, it makes a huge difference in understanding.
It really does. And here's a final thought to leave you with, building on what we've explored. Considering that models trained on structured data find effective solutions far faster than simply memorizing random data,
Right.
And given the potential for complex ideas to be encoded through superposition across many neurons rather than in clean individual units, what does this tell us about the actual nature of the knowledge and understanding these large models possess? Is it just incredibly sophisticated pattern matching on an immense scale? Or is something akin to feature extraction or even a form of conceptual representation genuinely happening just in a way that's foreign and hard for us to visualize directly?
Yeah, that certainly gives you pause for thought. Is it finding meaning or just incredibly good at mimicking it based on statistical patterns?
Exactly. Something to mull over.
Well, thank you for sharing your sources and joining us for this deep dive into the Transformer.
My pleasure. It was fun to unpack.